Hello everyone, welcome to all of you. So in last class we have studied about the simple form, simple scheme and how to code the simple form in OpenFoam that we have studied in last class. Now in this tutorial we are going to solve the simple scheme for the compressible kind of flow. Okay. So remember in the last class we have assumed that the flow should be incompressible, only then you can use the simple form. So incompressible flow means the match number is very low. Generally, if the match number is less than 0.3, then we can consider the flow like the incompressible flow. But if the match number is larger, then we cannot assume the incompressible assumptions. So for that purpose, we have to use the compressible kind of solvers. So here we are going to understand the solver for the compressible flow. So here we are assuming the steady state again. Now, there are two kind of solver available in the OpenFoam for solving the compressible flow, named as the pressure-based solver, and second one is the density-based solver. So remember always, if the match number is lower, then only you can use the pressure-based solver, and if the match number is very high, for that purpose you can use the density-based solver. So it does not mean that you cannot use the pressure-based solver that for the high match number, but if you compare the accuracy of both type of solver, then the density-based solver gives the accurate result. So that's why for a high match number, we always use a density-based solver. And pressure-based solver is generally take low computational cost and computational time. That's why it should be preferred. But when we talk about the higher match number, then accuracy is not so good. That's why for higher match number, we use the density-based solver. Now, if we compare for the steps, so here we are again going to solve the momentum equation for finding the initial velocity, and pressure correction equation will be used for correcting the pressure. And here remember that we are solving the momentum, continuity and the energy equations. So this is the uh, steps of the pressure based solver. And if you talk about the density based solver, here we are going to solve the momentum equation again, and here we are going to get solve for the density using the continuity equation, and from the density we are going to predict the pressure using some state equations. So this is the density based solver. So in this tutorial we are going to just focus on the pressure based solver. Maybe in the next lecture I will talk about the density based solver. So in OpenFoam, if you talk about the pressure based solver, so this is the famous solver, that is the rhoSimpleFOAM. So these are the equations we are going to solve. This is the continuity equations. If you remember, this is the Navier-Stokes equations. For pressure, we are going to solve the pressure corrector steps. If you talk about the pressure based solver. Now let's talk about some energy equations, because here we are going to use the energy equation for finding the viscosity, compressibility, or the density term. So this is the energy equations which we are going to solve in the OpenFoam. If you remember the law of conservation, we know that total energy of isolated system always remains constant. So using these principles, we are going to balance all the energy. So there are generally two kind of energy involved. That is the mechanical energy and that is the thermodynamic energy. So there are different form of the mechanical energy, that is the rate of change of kinetic energy, which is due to the velocity of the fluid, strain energy and the potential energy. So these three kind of energy is the in the form of the mechanical energy. And if we talk about the thermodynamic energy, so that will be due to the internal energy, heat flux energy, and if there is any source, that is the heat source, or it can be also the turbulence source. So any kind of energy will be there, then this is the source term. Okay, so this, if we write all these terms in the form of energy equation, this is the general form of the energy equations. So same that energy equation we can write in different forms. So like if you want to write in the internal energy form, so this equation you can write here, and this is if you want to write in the form of the enthalpy, then this equation you can write here. and the same equation you can write in the form of the temperature equation. Okay, so remember this in open form that internal energy or enthalpy form you can choose by yourself. So there are different thermophysical model present in the open form, and out of those thermophysical model you can choose that what kind of energy you want to solve. So when we go to the open form terminal, then I will explain that how you can choose this internal energy form or enthalpy type of form. So I told you that there are two kind of solver, that is a pressure based solver and density based solver. So pressure based solver is the segregation method and density based solver use a coupled method. So this, what is the segregation and what is the coupled method? It itself is a separate topic, but for now you should just know that this pressure based solver uses the segregation method and density based solver uses the coupled method. Now, what are the modification we are going to do in rhoSimpleFOAM if we compare with the simpleFOAM solver? So there is one addition of energy equation. So using in earlier simpleFOAM, the rho and viscosity and other physical quantities are the constant there. So that's why we have assumed that incompressible flow. So when the flow is incompressible, then density is constant and of course viscosity is also constant. But if there is energy, so there will be some form of energy will be transformed into the another form. So there will be, of course, the properties of the fluid will also change. Now using the equation of state, and we will calculate the compressibility, and then we will find the density, and that density will related to the temperature and pressure also. And again there will be modification to the pressure correction equation, and of course the boundary conditions. Okay, so these are the some modification we are going to do in the simple form for coding the rhoSimpleFOAM. So we are assuming the steady state, so that's why this unsteady term will be cancelled out. So we are only considering the internal energy form of the equations. So the way I will do for the internal energy, similarly you can do for the enthalpy energy also. And we will go to the solve this energy equation, then we will calculate the T, that is the temperature, and from that temperature we can find out the compressibility, viscosity, and the of course the diffusivity of the fluid flow. Okay, now we will solve for the pressure. That will be step 3, that is the pressure character step. And using this pressure character step we will update the pressure, and of course we are going to update the velocity. And using this updated pressure and compressibility we have to find out, we are going to update the density, and this will be iterate one by one until and unless our tolerance criteria will be fulfilled. So for simplification I have written here. So now let's go to the derivation part. So if I revise you from the last class, so this is the derivation we have done for the simple scheme. So this is the continuity equation, this is the momentum equation, and this derivation we have done for the simple scheme. Okay, so remember I told you that here while we are driving this rho will be divided to the pressure, and similarly here will be the mu by rho, and this rho will be also divided into this source term if there is any source term is present. Okay, so remember here we are solving for the p by rho, but in rhoSimpleFOAM we are not no longer going to solve for the p by rho, we are going to solve for the p only. Okay, so this modification we are going to do. So this derivation part I have copied here. So here this manipulation you have to remember that here we are solving for the p, and this step, that is the pressure character step, we are going to add the rho here. Okay, so this rho has been added here, and here while we are deriving this, or you can say that while we are forming the matrix here in these equations. So here this p by rho is not present here, here it is, we are solving for the p only. So these two modification we have done for the rhoSimpleFOAM. So these are the steps we are going to follow while coding the rhoSimpleFOAM. So first we are going to solve for the velocity using the previous density and previous viscosity and previous pressure. Okay, so this here we will find the u, and when we find the u, then we are going to solve for the energy equation. So remember, there are different thermophysical packages present in the OpenFoam. So we are not going to code the energy equation. We are just going to use those thermophysical packages. I will discuss about that. What are the different thermophysical present in the OpenFoam and how it has been coded, that we are going to discuss here. So using this energy equations, we will find the compressibility, viscosity, and diffusivity terms, and then we are going to solve for the pressure character step. So here we will find out the pressure field. So it should satisfy the continuity equations. So here again remember that this capability of the u equation dot h and u equation dot a. So these things we can easily access in OpenFOAM. So these two functions we are going to use while coding this. And then when we find out the pressure, we will use this equation to update the velocity. And when we update the velocity, so using the pressures we have find in step 3 and the compressibility we have find in step 2. So using these two quantity, we are going to update the density also. Now this updated density, updated velocity, updated pressure, viscosity, this all quantity is going to the input in the step 1, and this all the 6 steps is going to continue until we will reach the tolerance. Okay, so these things we are going to code in the OpenFOAM solver. So I hope these steps are clear to you. So let's go to the OpenFOAM terminal or Ubuntu terminal. So hello friends, now we are going to talk about the rhoSimpleFOAM and we are going to code it. Okay, so if you remember in last class we have coded the simpleFOAM scheme. So I am going to copy codings from the last class and we are going to modify that simpleFOAM into the rhoSimpleFOAM. Okay. So for that purpose, I have typed OpenFOAM 6. So I have created the environment of OpenFOAM 6. Now I will type foam new app understanding row simple foam. So we have created one directory, that is the understanding the row simple foam. Now before proceeding further, we should check once that everything fine or not. So I've typed wmake, and if it will compile correctly, it means that our solver is okay. So to do the modification, what I will do, I will also open the rhoSimpleFOAM which is already present in the OpenFOAM 6 directory. So in that way we can easily relate the things. Okay, so let's open the directory. So this is what we have created. Okay, so this is the folder we have created, understanding rhoSimpleFOAM. Let's copy some codes from the last class also. So this is the last class we have created the solver understanding simpleFOAM. So I can copy this createFields.h. I am copying this createField.h from this folder to the our folder. So we have copied the createFields.h, and let's see what else we can copy. So we can also copy the simple control.h from this code from the simpleFOAM to the rhoSimpleFOAM. So we have copied the simple control.h from this folder to this folder. Okay. And other things we can copy these things because these things we are going to use here also. So remember, this is also the simple based approach. So most of things is going to the similar to the simpleFOAM. So that's why I am copying most of the things from here. So this create fields all .h also we can copy here. And let's copy the code also. Okay, this codes we are going to modify some of the lines here. So let's copy the other codes also. Okay, so these things we have copied from the last class. Now let's again compile and okay, so I think we have included two times. Okay, so if you find this code, this error, redeclaration of the something. Okay, so if you find any times while you are compiling any code or library, say this redeclaration error, if you are seeing on screen, that means that you are declaring something twice. Okay, for example, here you can see that we are declaring this two object two times. Okay, so since we are declaring it two times, that's why the error is saying that we are redeclaring the object, that is the set root case dot object dot h, and here it is saying about the control dict. Okay, so we have to remove one of the these two object. Okay, so we can remove the header file. Now if you compile the code here, okay, so everything has been set up. Now we can do modification based on what we have discussed on the slides. Okay,
So if I open the createFields.h, so here you can see here that there are some variables like p, u, phi, p-old, transport properties, mu, fb solution, and these are the variables for setting up the reference and the for relaxation factor. Okay, we are going to use some thermal package, and from those thermal package we are going to find out the viscosity, density, and the other variables. Okay, so let's copy one thermal package. So this is the understanding rhoSimpleFOAM. Now we are going to first add the header file for the thermal package. So for that purpose, I have added fluid thermo.h thermodynamics. Okay, so this package I have added for the thermodynamics. Now we are solving the turbulence here also. Last class we have solved the laminar flow, but here we are going to add the turbulence model also. So for adding the turbulence model, I have copied this header file, turbulence model. Okay, so we have copied the fluid thermo.h for energy equations, and for turbulence model we have copied the turbulent fluid thermo model.h. So let's go to the create field. First add the thermophysical model for solving the energy equations. So these lines of codes, we are going to obtain the thermophysical properties. Okay, so it will construct, this is called as the selector. Okay, so there are two kind of method you can select any object, that is the selector, on another one is the constructor. So here we are using the selector method, and we are creating p thermo, okay, object, and after creating the p thermo object, we are storing the everything of the p thermo into the thermo variables. Okay, so this header file we have added. Okay, so whatever functions or whatever the variables or whatever the properties is present in this model, we can obtain using the object name thermo. So this is the physical this is the creation of the one object of the thermophysical properties. Now this line I've added, okay, it will check that whether this thermophysical properties, either you are solving for the enthalpy or the energy. Okay, so if you are using this thermophysical properties model, then you can only solve for the enthalpy or energy. So this is being checked here. Okay, now let's talk about the field. Okay, so p field is related to density. Okay, so I told you that for p field and rho and temperature, these things are related to the or energy equation. So therefore we don't need to create a variable like this for the p field, we can simply talk like this. Okay, so we will accessing the p field from the this thermophysical model. Okay, this p field is already, if you are calling this function, this p field is already has been defined in this thermophysical model. Okay, so maybe we can go to this thermophysical model, then you can relate this. So let's understand these lines, this thermophysical properties, and how, what is this validate is doing and what is this p thermo is doing. Let's go to the doxygen and understand this. So I have typed the OpenFoam 6 doxygen, and if I open this, it is open like this. Now if I type this one, so this has been opened. Now let's me go to the fluid thermo.h header file. So if I go here, fluid thermo.h, so it will give me some suggestion. So it is given with this suggestion. So here you can see here that it is fluid thermo.h has been derived from the basic thermo.h and compressible transport model.h. Now if I go to the source file, so here you can see here that this fluid thermo has been derived from the two class, that is the basic thermo and compressible transport model.h. There are some constructor. Now we are using this selector. Okay, for creating this object, we have selected this selector. Okay, so first we have selected this one. Okay, you can see here that the phase equal to word equal to null, so there is no required to give the information about the phase name or word. Okay, so now if you go to the further, you can see here that this compressibility variables you are obtaining here, the viscosity is obtaining here, and the so kinematic viscosity is also obtaining here. So this all the variables you can obtain using this thermophysical package. Okay, now about the pressures, speaking about the pressure, so this basic thermo.h is also accessed in this fluid thermo.h. So you can also access all the functionality of the basic thermo.h. So if you go to the basic thermo.h folder, and if I open the source here, so you can see here that volume scalar field pressure is already defined here. Okay, this functions is directly this thermo.p. so you have created the object the thermo, and using this object you are obtaining the pressure field here, and you are storing this pressure field into the p. Okay, so this is the way of creating the pressure inside the rhoSimpleFOAM. Now let's define the density field also. So in earlier the density was constant, and we have already divided the density into the pressure. That's why we have not created any variable of the density here. Now but in this case, in rhoSimpleFOAM, we have to access the density. So we have defined this density field. Okay, and you can see here that we are also obtaining the density using the thermo.rho. Now you are wondering that why we are accessing thermo.p like this and thermo.rho or density field like this. That is because of the way it has been implemented in this fluid thermo.h header file. Okay, so the way it has been implemented, so that is the why this is the way of accessing the pressure field and the rho field. Okay, so for that you can go to this header file, and maybe you can check that how this rho field has been implemented in that header file, and this pressure field has been implemented in this header file. Okay, now velocity it will be similar to the simpleFOAM only. The next variable is the phi field, and remember that here we have to also take care of the density also. We have to include the rho field also, so that will be linear. We are interpolating rho and u linearly onto the mesh surface vector, and we are taking the dot product of these two quantity. Because our density is no longer is constant, so that's why we are interpolating rho u and mesh surface vector. Okay, so this is the way of creating the phi field. We are again storing the p world, and this from this p field we have obtained here. Using that p field, we are storing the p world, that p variable here only. And again, here we don't need to call for the mu, so I am deleting this. So we are not creating any dictionary like transport properties, and we are not calling any viscosity, because we are obtaining the viscosity from the thermophysical model we are using here. Here we are also going to talk about the turbulence model, so that's why we can call this turbulence model here only. And this turbulence model will be taking the variables like rho u and phi and this thermo, and from these things it is going to adopt the turbulence model here. Now one most important variable that we are left to, that is the compressibility. Okay, I create the variable like volume scalar psi, that is the thermo psi. So these are the variable we have created here. Now let's go to the solver. So we are going to update the rhoSimpleFOAM scheme based on the simpleFOAM. So first thing, we will start with the simple loop, similar to the last class, and then we are printing the runtime name, and then we are going to solve like this only. Okay, so this convection term minus diffusion term minus pressure gradient term. Okay, so remember, the only difference between this simpleFOAM and rhoSimpleFOAM is that here this will not p by rho, here it will be only p value. Okay, so this equation will be same, only we have to take care of these things, that this should be p in the test case only. Okay, so I am just commenting out these equations, and then this equation will be solved, these equations, and then let's include one energy equation.
So before going further and write about the energy equations, let's first compile the and let's see what error it is showing. So I am turning off this everything after the E equation. Let me compile it first. So I have 6 and wclean.r and wmake. So here you can see that it is not finding the file fluid_thermo.h. Okay, so because in make folder we have not included the files which can recognize this header file, that is the fluid_thermo.h. Okay, we have to add the location where these two files has been already compiled, and as a compiled library it is already present. Okay, so this aspect we have to add in the this option folder. So what I will do, I will just go to the rhoSimpleFOAM, and I will go to the this option folder, and maybe I can copy all these things. Okay, so that way I can access the all the libraries which has been necessary for compiling our solver. Okay, so now if I go to the folder, and now if I do the wmake, so it is giving the warning that this variable has been declared but has not been used here. Okay, so this is just a warning, not some compilation error. Now you can see here that everything is working here. So now we can start editing the energy equation based on our equations. So for energy equations, what I'm going to do, I'm just going to copy from the rhoSimpleFOAM, and I will explain each steps one by one. Okay, so I'm going to just copy these equations, and we will going to keep only those terms which are important for the our case. So this complete thing I have copied here, and I have pasted here from the rhoSimpleFOAM. Okay, now we are not adding any source term, so I'm just removing this every option because we are not adding any source term. So these things I also removed, and this correct is also not required because we are not using the FB option capability. So what is doing, it is just copying the one capability, one method of the thermo object which we have been created, and that object is the HE, and it is storing into the variable that is called as the HE. Okay, now whatever we are going to access about this thermo.he, we can just call this name HE and we can print here. Okay, so maybe we can just, let's see what this HE name is printing here. So this will print the what this HE name is doing here. Okay, however before that, let me show you that what is this function from the OpenFoam doxygen. Doxygen we have opened earlier. Now if I open the .h fluid thermo.h file, so here it is the basic thermo.h that is already been part of this fluid thermo.h. And if I open the definition here, fluid basic thermo.h, so here you can see that he function has been declared here. So it is solving for the enthalpy or internal energy. So this is solving here enthalpy or internal energy equations. Okay, so to solve the energy or enthalpy equations, we are asking this name, that is the thermo.he. Okay, and let's see what it is showing here. So let me first compile this. So there is some error of semicolon bracket. So again we have just started the bracket but we have not closed. That is what this error is mean. Now if I compile here, it will compile. And so I am copying this test case from the rhoSimpleFOAM tutorial. So if I open in the terminal, I can start with creating the environment of OpenFoam 6. Now block mesh. So meshing has been created. Now we can run our solver here. So this is the solver we are creating. So this alpha is not defined. So in every option, every solution, we have to define the alpha. And let me define the alpha here, 0.3. And what wills variable we have created? This pref cells and pref value. Okay. So this solver has been started, and you can see here that it is printing the HE name equal to E. Okay, so when we call this thermo.he, so it has been called the HE function, and here if you print the HE name, that is going to print the name of the energy equation, that is solving the energy. E means there is a two capability, that is the H, that H is for the enthalpy, and E is for the internal energy. So remember I told you that the energy equations in OpenFOAM you can solve either in the form of the enthalpy or in the form of the internal energy. So how this compiler know that what form of internal energy you want to solve? So for that purpose, you can go to the constant folder, and in this thermophysical properties, you specify that here what form of energy you want to solve. Okay, so maybe you can put here the test, and you can see that the what are the different type of the capability presenting. So you can here see that. Okay. Okay, so here you can see that all the different form of the fluid thermo packages are seen here. Okay, so if I open here that, you have to enter the different type. So this is the type, like you can enter the S H psi thermo and H rho thermo. So different types you can enter here, and this is the mixtures. Okay, so what type of mixture you want to solve. So generally in most of solver I saw the pure mixtures, but also you can solve with the homogeneous mixture, multi-component mixture type of capability. Okay, this transport equation, so like the transport variables like viscosity and other physical properties, what type of equation you want to solve. So different type of keywords are present here. So like you can use the constant, you can use the Sutherland, you can use the polynomial. So these things you can enter here, and this is the equation of state. So this is for the equation of state. Okay, so there are perfect gas, rho constant. These things are entered in this equation of state package, and this is the species, that is the similar thing for all the cases. So here you are specifying that what kind of energy equation you want to solve. So, okay, so if I enter here, specific enthalpy, sensible enthalpy, sorry. So if I enter here sensible enthalpy, and then if I run the command here, so here we have to enter the SI thermo. So again, if I run the solver here, so here you can see that now the name is suggested like H. Okay. So when you put here sensible internal energy, then it is going to solve for the E, that is the internal energy. And when you put here the sensible enthalpy, it is going to solve for the H, that is the sensible enthalpy. Okay. So this is what we are doing here. So now let me turn off this, and let me delete it. So next line. So we are creating one matrix, that is the E matrix. Okay, E equation matrix, and here first term we solve for the that phi and in He. He means that can be either enthalpy or the internal energy. So that is the convection term. Okay, so phi we get in the createField equations. We phi get by interpolating rho u and mesh surface vector. So this term we get in here, get from here, and this He can be either internal energy or sensible enthalpy. Now second term, remember that varies for if you are solving for the enthalpy energy or if you are solving for the internal energy. So for that purpose we can write this like that. So we are checking that whether this He name equal to E or not, and based on the condition it will going to solve for the either the enthalpy equations or the internal energy. So now let's check the condition, how this condition works. So this is checking here whether this He name, that is the thermo.H, it is showing the name here from this thermophysical properties folder. So from this folder it is checking that what kind of energy it is going to solve, and if this He name is matches with E, then it will solve the internal energy equation. If this is not matching with the E, then it is going to solve the enthalpy kind of energy equations. So let me compile it and let's see how this condition works. So solver has been compiled, and maybe we can run in the test case. So here you can see here that it is checking that He name equal to H, and if this name matches, then it is solving for the enthalpy. Okay. So let me open the solver here. So you can see here that we are printing first He name, then He name is equal to H because in thermophysical properties the energy is the sensible enthalpy type of energy equations. So it is checking here and this name is printed here, and this condition is being checked. If this is matches with E, then it is going to solve the internal energy, but here it is matching with the H, that is why it is going to solve the enthalpy energy. Okay, so similar condition, first solve the first equation, that is the phi into E or phi into H. Okay, second term, so based on the condition similar to here, so it is either going to solve this equation or it is going to solve this equation. So it will either solve this equation if H name equal to E, that is the internal energy. If it is the enthalpy, then it is going to solve this, that is the enthalpy. So I'm just turning off this condition here. Now this is the turbulence term. So if there is the energy due to the turbulence, that is added like this. Now this is the E equation dot relax. That is the way of providing the relaxation factor in OpenFoam. Okay, so either the way we have done here. So remember in last class we have done this kind of thing. Okay, so you using this equation, this function E equation dot relax, you can provide this kind of relaxation factor. Okay, now we are solving the equations, and this thermo.correct, this is the option. After solving this energy equations, it will correct all the thermophysical properties. Okay, so like I told you that from energy equation the density, no, sorry, from the energy equation the compressibility, the viscosity and other terms are being corrected. So this is the line where it is going to correct the all the variables related to energy. Okay, so I hope this energy equation is clear to you. Okay, we are including this equation with this command. Okay, so our UE matrix has been created, UE matrix has been solved. Now we have solved the energy equation, and from that energy equation we have updated the all the properties related to energy, that is the viscosity, compressibility and diffusivity of the fluid flow. We are going to solve for the simple scheme. So these two functions we are going to still use, that is the UE equation dot A and UE equation dot H, and I already told you that what these two functions and what are these two methods in last class. So we have already coded the energy equation and we have already started with the velocity. Okay, so velocity matrix we have created. Now it's our turn to implement these simple schemes, and the modification from the simple form is very to only add the row term in that equations. Okay, so this is the steps we are going to follow. So here we will start with the pressure corrector step, then we will update the velocity, and of course in last we will update the density also. Now this A scalar field we have created, that is the equation dot A, and this H we have already created. That this A inverse will be also required here. So we are also calculating the A inverse, which is the diagonal elements of that complete U matrix. Okay, so this A inverse we are calculating here, and I told you that it is very easy to calculate the inverse of a matrix diagonal elements. Now in this term, this A inverse must be multiplied with the row field. Okay, so remember here in simple form there was only concept of the A inverse, but in row simple form there is a interpolation of row and then multiply that row with the inverse, so that will called as the row A AU. Okay, so we are creating this field. So we have created this volume scalar field, that is the A, that is E equation dot A, and then volume vector field, that is the H, and we are taking inverse, that is the matrix we have formed here in the left side, and after that we are interpolating the row field and multiplying this by ARAU. Okay, so this equation we are going to solve. So here you can see that the row has been multiplied with the A inverse and then with the del P. Here also you can see that row is multiplied with the A inverse then H. Okay. So these things we are going to apply here. So we will interpolate this row with the A inverse. Then we will take the dot product of these two quantity, and then we will multiply with the del P, and here we will multiply with the HU. You can see here that we have taken A inverse. Okay. Now we have multiplied this row with RAU. So that is the interpolation of row on the faces, and then we are taking the product of these two quantity. Okay. So this is the row RAUF. Now we will also calculate the this quantity, that is the H by A, and now this is RAU. So I am just replacing this A inverse with the RAU. So remember these two things are similar, just the naming is different. Earlier we were calculating A inverse, now here we are calculating the RAU, and then we are multiplying with the H. Okay. So these things we have created. Now again we can calculate the surface scalar field for the H by A. So this is the phi H by A, and we are again see here that we are multiplying the interpolation of the row with the flux of the H by A. Okay. So these things we have created for the phi H by A. So this is the for the right term of the P equation, and this is for the left term of the P equations. Okay. So this is the interpolation of this. Now we are going to just write the P equation. So for P equation we are going to solve this. Okay. So this is row. This we have created this two multiplication, and here also we have created this two multiplication. So we are going to apply these equations for solving the P equation. So from the slide you can see here that with P, now this term that earlier it was the A inverse flux, now it has to be phi H by A with this equation. So this term will be multiplied to the del P, and this term will be multiplied to the this HAU. Phi H by A should be written here, and this pressure rho RHAUF will be multiplied with the pressure. Okay, so this is the equations for the P equations. Okay, so we are ignoring the source term. So this P equation has been written, and this you are setting up the reference value for the pressure. So and now after that we are solving for the P equations, and we are providing the relaxation factor if any relaxation factor is there. Now we have to update the velocity here. Okay. So here U equal to H by A, that is the same term, A inverse into H. This is the similar term. So that we can write here H by A. Now this A inverse we have calculated like RAU. So A inverse we have calculated like RAU. So we are replacing this A inverse equal to RAU. So this is the step where we are going to update the value of U. Okay. Now we again need to the calculate the phi. So here we have created the phi field. So similarly we can copy from here and we can paste here. So this is the way we are calculating the phi term. Now we will update the U boundary condition and P boundary condition, and for relaxation factor we will store P volt equal to P, and then we will type the run right. But before that, one step very important, as I told you that row will be also updated here. So we will also calling the row equal to thermo.row. Okay. So this is updating the density of the fluid flow. So this is the complete simple scheme for the compressible flow. So that is the name of the rhoSimpleFOAM in OpenFoam. So you can see that some steps that I've discussed, that we are solving the energy equation here. That is the pressure based approach, and maybe let's compile. So some error is there in E equations. So in 20 line. Okay, so this equal to sign should not be present here. Okay, so these things we have coded here. So there is only one warning, that we have declared one variable, that is psi, and we are not using the variable. But you remember that this psi term will be when you are using this in energy equations, when we are solving this thermo.correct, it is automatically taking care of the psi term, and it is updating the value whatever needed here. So this don't need to declare this variable psi in our solver. Okay, however, if you have some source term like every option terms here are in momentum equation, then you need to use this psi term here. Okay, so but in this is a simple example, this is a simple solver, that's why we are not using this psi. So we have compiled the solver correctly, and all the steps I have explained you in this row simple form. And since the video is already longer, so I think in next tutorial I will going to compare you this solver with the row simple form. Okay, so this present solver and the row simple form we are going to compare, because here you can see here that the simple consistent term is there, PC equation term is there. So this different term I am going to explain you in next tutorial. And also we are going to develop a test case, and we are going to compile the test case using the solver we have created here and the solver which is already present in the OpenFoam. So we are going to do these two aspects of this solver. So I hope this tutorial is helpful for you, and I hope that you have some idea about how this row simple form works. So next two lectures will be only dedicated to the compressible solver only. So in next tutorial maybe I will talk about the I will going to compare about this row simple form and our solver, that is the understanding row simple form. And after that we are going to talk about the density based solver. So thank you to all of you for watching this video, and please subscribe and share my YouTube lectures. Thanks to all of you.